Hello, everyone. My name is Shreesha, and today I'll be talking about our work, low end-to-end latency atop a speculative shared log with Fix-Ante Ordering. This is work I've done with my colleagues, Tony, Xuhao, Jiyu, and our advisors, Aishwarya and Ram. So shared logs are widely used by today's real-time data-driven applications. These applications use the log as a durable and ordered sequence of records that decouples the upstream producers from the downstream consumers. And these applications care about minimizing the amount of time they take to derive insights from the stream, that is their end-to-end latency. While shared logs have been very well studied with many works such as Corfu, scalelog, Boki, lazylog, and many more systems, today shared logs incur high delivery latencies. This delivery latency refers to the time taken by the log itself to make the record ready for consumption at the consumer after being produced. And this high delivery latency, unfortunately, delays the start of the computation at the application, which can also affect the application's end-to-end latencies. We find that the cause of the high delivery latencies is that the shared log takes a lot of time to order records. Now, given that the high delivery latency stems from the expensive ordering cost, we note an opportunity for speculative execution. And to this end, we designed the SpecLog abstraction, which is a new speculative shared log abstraction that allows the speculative consumption of records by predicting their global order. This allows the application to begin its computation earlier, and the application can overlap its computation with the global ordering at the shared log. And finally, the shared log can confirm the order, and the application can then expose its results. So by effectively overlapping the ordering and computation, the application realizes low end-to-end latencies atop SpecLog. So any speculative technique, it relies on the nature and frequency of misspeculations. And our key innovation with SpecLog is how we virtually eliminate misspeculations except in extremely rare scenarios through a technique called Fix-Ante Ordering. So Fix-Ante Ordering is an idea where we essentially predetermine the global order that the system will produce, which enables easy prediction, and then we make the system adhere to that order. So to summarize our contributions, we have SpecLog, which is a new speculative shared log abstraction, which uses Fix-Ante Ordering to enable near-perfect speculation. And Belfast is an implementation of the SpecLog abstraction and the Fix-Ante Ordering idea. And Belfast addresses several practical challenges that arise when implementing this idea. Belfast does this while enabling low end-to-end latencies and retaining the benefits that today's shared logs give you. Finally, we built 3 prototype applications: fraud detection, intrusion detection, and high-frequency trading, and show that they get end-to-end latency benefits atop Belfast. That was my introduction, and here's an outline for the rest of the talk. With that, let's get into the motivation for SpecLog. So shared logs give you a simple append and read interface. And for streaming-based applications, it's often desirable to have a subscribe interface, which lets you stream the records. Now, shared logs do this while giving you strong guarantees of durability and linearizable ordering. In this context, linearizable ordering means that if an append follows another in real time, then the shared log will respect that real-time ordering. Shared logs do this while storing their records over one or more storage shards, which are each a fault-tolerant group of nodes. And the job of the shared log is to essentially give you a total order across the shards. Now, today's state-of-the-art shared logs adopt something called the durability-first architecture, which was first introduced in scalelog. Now, the idea in the durability-first architecture is that upon an append, a record is first made durable at a shard of the client's choosing, and then ordering happens later in a batched manner. That is, the shards periodically contact a fault-tolerant sequencing layer and report their local progress, and the sequencer stitches together a global order across the shards. Now, this durability-first architecture has many benefits. For example, it gives clients the ability to flexibly append their data to whichever shard they want. It also gives the ability to seamlessly add or remove a shard on the fly. And finally, applications also get scalability to meet their requirements. Now, because of all these benefits, the durability-first architecture has since been adopted by other works, such as Boki and FlexLog. But unfortunately, the durability-first architecture suffers from high delivery latencies. Let us take a look at the path of a record from production to consumption in ScaleLog and understand why. So upon an append, the record is logged at the shard primary, which makes it durable by replicating it on a backup. Periodically, the shards contact a central sequencing layer, reporting with the length of their local logs. Now, since this step happens periodically, this incurs a delay. The sequencing layer primary collects these reports across the shards and creates something called a global cut, which is essentially a global snapshot of the progress of the system. For fault tolerance, this cut is replicated on the sequencing layer backups through a standard replication protocol, such as Paxos or Raft, and this incurs an additional delay. The global cut is then forwarded to all the shards, who, using the global cut and a lexicographic order of assignment across the shards, assign global positions to their local records. And only after this point can a downstream consumer actually consume the record, or can the append be acknowledged. So it is clear here that the problem comes because of the expensive ordering protocol across the shards. Unfortunately for the real-time applications, this expensive ordering, which results in the high delivery latency, also delays the start of the computation at the consumer, which affects the application's end-to-end latencies. So to give a concrete example, if you consider a fraud financial detection application, a delayed consumption means the delayed start of the computation, which could involve matching the transaction, the details of the transaction with the user's history or prior behavior, and it potentially delays flagging of financial fraud. And there are many such applications that care about their end-to-end latency. For example, you have real-time analytics, high-frequency trading, fraud and intrusion detection systems. And for many of these applications, even saving milliseconds in latency can have huge impacts. And it is natural, therefore, that these applications demand a low delivery latency from the shared log. It is not so surprising that in a 2023 streaming report by Red Panda, up to 35% of the industry practitioners reported that they primarily care about the delivery latency of their streaming system. So reducing delivery latencies is important for these class of applications. With that, let's see how SpecLog addresses this problem. Given that the high delivery latency stems from expensive ordering, SpecLog identifies an opportunity for speculative execution. That is, if the shared log can quickly deliver the records after it has been made durable by speculating the global order, this allows the application to begin its computation earlier. The application can then overlap its computation with the global ordering. And finally, after global ordering, the shared log can confirm the order, and the application can expose its results. So by effectively overlapping the compute with the ordering, SpecLog lets you achieve low end-to-end latencies. Now, to enable this speculative abstraction, SpecLog presents the following interface. For appends, SpecLog's appends return after global ordering, just usual to any other shared log, with the position of the record in the global order. For consumption, SpecLog allows a speculative consume. That is, it has a speculative subscribe call where the stream of records has the speculative order. Finally, SpecLog has new interface calls to either confirm speculations up to a position or to fail speculations beyond a position. So these are callbacks that you receive from the log. Now, applications have to adjust to this, right? So what applications have to do is that they require a few minor modifications. Firstly, they have to they have to manage state. That is, they have to maintain state of the unconfirmed changes that they've made to their application. And they need to listen to these confirmations and failures. So upon a confirmation, the application can expose results up to the position specified in the confirmation. And upon a failure, the application has to roll back its state and recompute from that point onwards. The challenge with SpecLog is that it is hard to predict the position in the global order, right? To take a look at this, let's see a concrete example. So let's assume this configuration where each shard has reported one record each, and there are 3 shards in the system. In such a scenario, the global order produced would be something like below. Now let's say that shard 2 received a new record f, for which it wants to predict the global position before ordering, right? So one option would be for the shard to assume that all the other shards are going to report the exact same number of records that they did the last time. And with that assumption, the global position of f, predicted global position of f, would be 4. However, in actuality, if shard 1 reported 2 additional records as opposed to 1, then the predicted position that of 4 for record f will no longer hold true, as the actual position would be 5. So the challenge here is that it is hard to predict these global positions when the shards have a free will to report as many records as they like. So to address this, we have a new idea called Fix-Ante Ordering. In Fix-Ante Ordering, we define something called predetermined cuts, which are essentially a fixed sequence of global cuts that the system is expected to produce. So it's determined beforehand, which is why Fix-Ante. To fix this, we fix a quota, which is a fixed number of records that each shard can report, right? Furthermore, the sequencing layer waits for the predetermined cuts to be met before sending the global cut and actually committing the records. So to give a concrete example, let's consider the same scenario as earlier, but now shard 1 has a quota of 2, and shard 2 and 3 have a quota of 1. In this scenario, the sequence of predetermined cuts would be 2, 1, 1, 4, 2, 2, 6, 3, 3, and so on. Since each shard knows the predetermined cuts, it knows the sequence of global cuts that the system will produce. Therefore, each shard can predict the positions of its records easily. For example, now shard 2 can predict the position of its record C to be 2, as it knows that there can be exactly 2 records behind it. Now, if a shard receives more records than its quota, then it can simply delay these records to a subsequent report, such as record E in this case. If a shard receives fewer records than its quota, such as shard 1, then the shard can pad its local log with no-op records to satisfy the quota and then send the report. Note that these no-ops have no impact on the application computation, and they can simply be ignored during consumption. So in both these scenarios, the predetermined cuts can be met. But this does raise a question. If everything is predetermined, why is there even a need for speculation? Speculation is necessary because if the shards meet their quota, then the predetermined order and the actual order produced after talking to the sequencing layer will be the same. And therefore, the speculated order is the same as the actual global order. In such a scenario, the speculation succeeds. However, if for some reason the shard is not able to meet the predetermined cut, then the final order will be different from the predetermined order, and therefore the speculation fails. Let us consider cases where this might happen. If a shard primary fails, right, then the shard, being internally fault tolerant, could still mask the failure by having the backup take over and report on behalf of the shard. So in such a case where shard internal failures can be masked, no misspeculations would occur, as the shard can continue to meet its quota and therefore satisfy the predetermined cuts. However, if an entire shard fails, or if an entire shard is partitioned from the sequencer, then in such a scenario, the shard will no longer be able to meet its predetermined promise, and therefore such a scenario will have misspeculations. Under such scenarios, the application would have to roll back and recompute. But fortunately, such scenarios where an entire shard fails, or that is an entire fault-tolerant group goes down, are extremely rare. And therefore, SpecLog can give you high speculation success rate, except in extremely rare scenarios. With that, let's take a look at the end-to-end record path with SpecLog. So the situation is the same as earlier, but now we have quotas, and Fix-Ante Ordering is enabled. Upon an append, a record is made durable at the shard, but now it can be immediately consumed with the speculated order, and the application can begin its computation. The usual shared log ordering happens in parallel with the computation at the application, and finally, after global ordering, the order can be confirmed at the application, and the application can expose its results. Therefore, by effectively overlapping the computation with the global ordering, you get low end-to-end latencies. Let's now take a look at the design and implementation of Belfast. So while Fix-Ante Ordering and SpecLog give you a general framework to enable accurate speculations, Belfast is an implementation of SpecLog that addresses several real-world challenges. For example, while SpecLog prescribes quotas, Belfast has to ensure that these quotas are right-sized. That is, if the quotas are too high, you have a problem. If the quotas are too low, you also have a problem. So the way we address this in Belfast is that the quota is set based on the rate of incoming records at the shard. Under bursty scenarios, to ensure that Belfast will not have a sustained end-to-end latency spike, we use something called a lag fix mechanism. To ensure that the quotas can be changed based on the rate at the shard, and that shards can be seamlessly added or removed on the fly, we use a speculation lease window mechanism, which ensures that both these scenarios can be handled without causing any misspeculations. And lastly, under whole shard failures, Belfast needs to ensure that the clients reliably get the misspeculations and that records for confirmed positions never change. And for that, we have a view change protocol. I will not go over these techniques in detail due to a lack of time, but please take a look at the paper for these details. With that, let's get into the evaluation. We asked 2 questions in this talk. So what are the end-to-end latency benefits of Belfast? And does Belfast benefit end applications? So for the end-to-end latency benefits experiment, we run a workload with 4 kilobyte sized records, where the downstream computation involves 1.5 milliseconds per batch of consumed records. Here, we see that by delivering records up to 3.5 times earlier than what SpecLog would do, Belfast can give you 1.6x lower end-to-end latencies. And this is the primary benefit of overlapping of early delivery and overlapping the ordering and compute. To evaluate Belfast benefits to end applications, we built 3 prototypes: high-frequency trading, fraud monitoring, and intrusion detection. Each of these applications are interesting in their own ways. That is, they have different compute durations, different types of compute, a different assignment of producers and consumers to the shard. But in each of these applications, we see that we have end-to-end latency benefits. So there are many more experiments in the paper, such as application evaluation under failure scenarios and misspeculations when they would have to do rollbacks and recompute. We also evaluate Belfast under bursts, rate changes. We also see how end-to-end latency is at scale when you have a lot of shards. The paper also covers many more discussions about Belfast. So please take a look at the paper for all these details. With that, I'd like to end my talk. Our artifact is publicly available on GitHub, so please take a look. Thank you.